Hi, everyone. So let's go ahead and take a look at question number 2 from your chapter 3 problem set. Question number 2 says that the pKa of acetic acid is 4.76. What is the value of the equilibrium constant, KEQ, for the following equation? So the first thing that they're giving you is a pKa of acetic acid. So CH3COOH to be 4.76. So remember, when you have pKa, that the P means negative log of something. So of the Ka of acetic acid being 4.76. So that begs the question, what is Ka? Well, that's the equilibrium constant of acetic acid, of the equilibrium point of acetic acid dissociating itself into hydrogen ions and its conjugate base. So it's referring to CH3COOH plus, so it's in water, that's the liquid, dissociating itself into CH3COO minus plus H plus creates protons. It's a Bronsted-Lowry definition in our solution. So that means that the Ka, so that implies that the Ka is products over reactants. The water is a liquid, it's in liquid form, so we don't include that in this equilibrium expression. We will for the overall reaction that we're looking at, but not in this. So this is going to be CH3COO minus, one of the products. I should have put H3O. So H3O plus all over our reactant, CH3COOH. So that's what Ka is. So once again, we're gonna plug all of that in. And so let's bring this down and I'll rewrite it. So negative of the log, it's base 10, right? Of Ka is 4.76. So we'll say the log base 10 of Ka is equal to negative 4.76, which means, remember, logarithms from whatever year in high school, neither do I, but this is how you do it. You just cross out the word log and you swing that 10 over to the other side, which means Ka is equal to 10 to the power of negative 4.76. And that means that our Ka is equal to approximately 1.738 times 10 to the negative 5. Now, if we look at what they're actually asking, the question says, what is the value of the equilibrium constant KEQ for the following equilibrium? So the equilibrium that they've given us is CH3COOH plus H2O, and this is the little trick because the water is part of this equilibrium. This is aqueous solution. Forming acid H3O plus CH3COO minus. So what is the equilibrium constant or expression for that reaction? So water is aqueous now. It's not a liquid solvent. So you have to include it in the equilibrium expression. So you have to put, obviously, products first. H3O times CH3COO minus over our reactants, CH3COOH times H2O. Well, this part, I'm going to highlight it in blue. We just did. Right? And we calculated that to be that. So all we're left with now is KEQ equaling, I'm not going to write the whole thing out, just Ka, whatever we calculated, over the concentration of H2O, which they've already given us. So it's okay, we'll write it out, 1.738 times 10 to the minus 5 over 55 molar. And that's going to give you an answer of KEQ equaling 3 point something, 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 but we just rounded to 3.2 times 10 to the 7, which I believe is answer choice A. No, it's not. It's answer choice D. Okay, and the second thing that we covered today was acid-base chemistry. Really, it was just one group of questions from your problem set that we were kind of able to get through, just one concept. And that was essentially trying to figure out which of the possible answer choices had the strongest acid. And we were basically wondering, is there a systematic way of figuring out what is the strongest acid versus weakest? And then can we just flip that around and say, what is the strongest base versus weakest base? And there is a way of figuring that out. So the very first thing you want to start out with is to identify which atom is losing its hydrogen, which atom is actually behaving like an acid. So I'm going to take a look at question number 7 from your problem set. And it says, which of the following is the strongest acid? So in answer choice A, they've given you CH3OH, which is methanol. So when this thing behaves like an acid, let me just draw this out. So here's CH3. I'm drawing it out in expanded form, OH. So I know you know that the hydrogen that is being liberated into solution is not one of the green hydrogens, but the yellow hydrogen. That's the thing that's going to go away as a proton. And when it does, it's going to leave behind the 2 electrons that form the bond. There's one of the oxygen, and here's one of the hydrogen onto the oxygen. So the CH3OH is the acid, and we're going to call it a Bronsted-Lowry acid because we're going to be looking at hydrogens that it's throwing off or accepting. Obviously, it's throwing one of them off, the yellow one. That one right there. So it's going to turn into CH3O minus, and then there's going to be a plus H plus in solution. Answer choice B gives you a CH3CHO. So that this is a little strange, but CH3CHO would look like this. So when this thing loses a hydrogen, it's still going to be that one right there, and not one of the methyls. So that's going to be CH3 CO with a minus on the carbon. So it would look like this. Answer choice C is CH3COCH3. So that's going to look like that. When this thing loses a hydrogen, it's going to be one of the hydrogens from the methyl groups on either end. So we're going to have CH3CO, COCH2. So it's going to look like, let me draw in the 3 hydrogens. And one of these is going to be leaving. So those electrons are going to go onto that carbon right there. So we're going to have something that looks like this, with a negative charge on that carbon. And then the last, plus H plus. So the carbon that's going to have a charge on it, if we wrote it out here, would be this carbon right there. And the last answer choice we have is CH3, COOH. So you guys are pros at this point. You probably know that that looks like that. CH3, COOH. So it's going to be this hydrogen that's going to be leaving. And we're going to be left with CH3COO, negative on the O. So it looks like that. So here's the important part. Now that we've figured out which hydrogens are leaving and where the negative charge is being left behind on which atom, the atom that has that negative charge left on it, that's the atom that you compare. To figure out what's most acidic, what's least acidic. So what are we comparing? I'll put everything in pink. So the thing that we're comparing to figure out what is most acidic and least acidic is going to be this oxygen with the negative charge because it lost its hydrogen. Compare that to that carbon with its negative charge because it lost its hydrogen, to this carbon, it lost its hydrogen, to this oxygen because it lost its hydrogen. So we're comparing everything that I put in pink and we're trying to figure out what's the strongest acid. So what are the rules for comparison? What is it that we go through systematically to figure out how we rank strength versus weakness? You do this in this order. The number one thing you look at is actually charge, but we're going to forget that for now because you'll never really have any differences in charge. So we're going to start with atomic size. And the simple rule we're going to follow for atomic size, if we're on our periodic table, is going up and down a certain group. Okay, so going up and down a column. That's all we're looking at to figure out size. The further to the top you are, the smaller you are as an atom. As you go down the periodic table, as an atom, you're bigger, just in terms of size. If you're big, that implies you have a long bond length with, let's say, a hydrogen atom, because we're looking at acids. So the thing you're bonded to is a hydrogen. And if you're a small atom, you have a short bond length to or with the hydrogen that's bonded to you. Short bond length means strong, tight bond with the hydrogen. Long bond length with your hydrogen means flimsy and weak. You can't hold on to your hydrogen very tightly because you're long and strung out. Like a wet spaghetti noodle, it's about to break anyway. That's the number one thing that we look at. The thing that I want you to get used to is drawing your periodic table this way. Just remember to write CNOF, carbon, nitrogen, oxygen, fluorine. They're all in the same row. Okay, they're all in the same row. And then your halogens go F, Cl, Br, and I. And if you want, you can put P and S right here under the nitrogen and oxygen. So take a look at the atoms we're comparing. We're comparing O's and C's, right? Answer choice A had O, B had C had C, and D had O. C and O are in the same row. They're in the top row. So you can't use atomic size to differentiate them. And even more important than the size of the atom was the charge, but they all have the same charge. They're all negative. So you can't decide what's, positive, neutral, and negative to say this is stronger or weaker as an acid or base. So charge is just, it's never a part of it. In this case, atomic size doesn't help us. So we go to the next criteria for trying to figure out what's stronger or weaker as an acid. And I should probably tell you that in terms of size, stronger acids are down here. And weaker acids are up here. Why? Because the bigger the atom, like let's say iodine. You know what, let me not use iodine as an example because this is where we had some confusion earlier today. Let's use sulfur. Sulfur is going to be a bigger atom than oxygen. They're in the same column. in the same group. So you're going to have, let's say, S bonded to an H and an O bonded to an H. The bond length between the S and the H is longer than O and H. So which one wants to give up its hydrogen more easily? The sulfur or the oxygen? So hopefully you said sulfur. So between those two, sulfur, sulfhydryl, is the stronger acidic group. And oxygen would be the weaker group in terms of it being an acid. So the sulfur is going to want to kick off that hydrogen very easily and become an S minus. And the oxygen is going to not really want to do that, at least in comparison to sulfur. But in this case, for problem number 7, we're given only oxygens and carbons, and they're in the same period, in the same row. So we can't use atomic size to figure out what's a stronger acid and what's a stronger base. So we go to electronegativity. That's the second determining factor. I know electronegativity rises as you go from bottom left to top right in your periodic table. So there's your periodic table, and it goes that way. For our purposes, we're only going to be looking at the horizontal, CNOF and FCl BRI. So electronegativity is going to be left-right. So you know fluorine is more electronegative than carbon. Now we can make our differentiation because we're comparing oxygen with carbon. So who's more electronegative? Oxygen is. Because it's more electronegative, it wants a negative charge on it as a preference. So if oxygen had to be O negative, it would be okay with that because it's more electronegative. If carbon had to be C negative, it would not really be okay with that. So I'll write this backwards. So if you had a CH and an OH, between the two, now who wants to give up the hydrogen more? So I hope you said the oxygen. So in terms of size up here, we said sulfur would beat the oxygen because it was a size thing. But in this problem, it's not a size thing. It's an electronegativity thing between the carbon and the oxygen. So in this case, oxygen wins. So we can get rid of anything that has carbon in it. So B is no longer an option, and C is no longer an option. So now we're comparing A and D. So A and D are similar because, again, they have the same charge. They're both negatively charged oxygens. They're the same atom, oxygen. So there's no comparison between atomic size or electronegativity. It's the same atom. So what is there to compare to? So we can't use atomic size or electronegativity. So we go to our third kind of breaking determining factor, which is resonance. And you guys reassured me that you know what resonance is. We didn't really practice that in the GSG today. But resonance is essentially being able to delocalize a charge, negative or positive, over the entire compound. So we were left with what? A and D, right? So A is just a CH3 with an O minus. and D was some kind of carboxylic acid with an O minus. So I hope you realize that there's no chance of resonance for A because the negative charge is not next to a pi bond. There's no pi orbitals that it can shove itself into, those electrons. With D, you can make resonance structures, or structure, I should say, because you can move these electrons over there, and then you can push the double bonded electrons onto that oxygen. And the resonance structure you can make is that thing. And that's what breaks the tie between A and D. So bye-bye A. So our answer is D. What if A and D were the same molecule? Not exactly the same, but in terms of resonance, they were the same. So what if I said A was also a carboxylic acid, and D was a carboxylic acid, with one tiny difference, which is A had a fluorine sticking onto it. Well, resonance is not going to go as far as the fluorine, so we've done everything we can do in terms of resonance. So when we go back to our list of priorities, we see that atomic size couldn't be used to figure out what's more acidic or basic because it's the same atom that we're comparing. That oxygen, right? Charge was the same, they're both negative. No issue of bond length or atomic size or radius or anything like that. No issue of electronegativity. And now resonance doesn't help us either because they both would make the same resonance structures. These two. So now how do we break the tie? That's when you go to something called induction. Induction is moving a charge through sp3 bonds. And induction is a function of electronegativity. Electronegativity of a different atom. And I think this is where maybe I wasn't being clear today, this is where the confusion was in terms of ranking acids and bases. So I'll redraw A and B again. So we're saying A was this thing, or A and D was just that thing. So induction is when you have an electronegative atom. In this case, we do have one. It is the fluorine in answer choice A. And because it's very electronegative, it wants to be negative. So what it's going to do is like a vacuum. It's going to take the negative charge on that oxygen and suck it through the sp3 bonds towards it, like literally through those bonds. So the formal charge on our pink oxygen is no longer -1. It would be like slightly less than that. It would be like -0.7 or something. I'm just making that up. But so the fluorine helped to stabilize the negative charge on that oxygen. So the oxygen is now getting help from resonance and from its electronegative buddy. Does D have that help from a friend? Nope, there's no electronegative atoms in D. So finally, we broke our tie. And we said that because of the inductive effect that other electronegative atoms can offer, if they're around, we would say that A is the stronger acid. And remember, we're saying that A is the stronger acid because remember, A came from that structure, and it created in solution this structure. So this was the acid, right? This was its conjugate base. So because the conjugate base was stabilized by inductive effects and resonance, it was a more stable conjugate base than any of the other choices that we had. Because it was more stable, if the acid were to ever dissociate and go in this direction, it would be okay with that. But it's not going to go in that direction and lose its hydrogen if the conjugate base was unstable. Who goes into more unstable scenarios? Definitely not nature. They go into more stable scenarios. So that's why you always hear that phrase, an acid is as strong as its conjugate base is as strong as how stable its conjugate base is. That's where that, saying comes from. There is one other thing that makes or breaks these ties, and it's the least important, but that is hybridization. And hybridization refers to the hybridization of the atom that we're looking at, the atom that lost the hydrogen in the process of it becoming an acid. So we're looking at the hybridization of all of those pink atoms that I originally drew, the O- and the C-. But in this case, there is no hybridization to talk about. So I'll have to just kind of make up a new problem. So let's say you had something like ethane. So CH3, CH3. Call that A. And then it's acting like an acid. So it's losing one of its hydrogens. So it becomes CH3, CH2, with that carbon being negatively charged. Then let's say we had a different molecule. Let's say we had ethene, ETHENE, right? Something with a double bond, CH2, CH2. And this thing becomes an acid, or it behaves like an acid. So it loses one of its hydrogens. So that carbon right there becomes negatively charged. It lost, and I should put in the extra electrons that become part of the atom, right? That's where the negative charge comes from. And now let's say we have a third example, ethyne, ETHYNE. So we'll say a triple bonded CH to a CH. And this thing behaves like an acid. Loses the only hydrogen that it had. What is the hybridization? So again, we'll go through all of our rules, and I'll zoom out as much as I can, if you can even see. So number one, remember, number one was atomic size. Well, there's no issue of atomic size because it's all the same carbon with the same charge that we're comparing. It's all just C with a minus. So we can't really compare atomic size because they're all the same atomic size. It's all the same atom with the same charge. We can't look at electronegativity either. It's just the same thing. We can't look at resonance because in none of these structures, A, B, or C, can you do resonance. Resonance is not really possible here. There's no inductive effects. I shouldn't say that there are, but just for the sake of learning, we'll say that there's not inductive effects. And if I remember correctly, in this case, the inductive effects are the opposite of having a halogen, like a fluorine or something. But we won't even look at that right now. We'll just say there's no inductive phenomenon going on in A, B, or C. So we have to look at hybridization. That's the only thing that'll determine what's more acidic and what's least acidic. So what's the hybridization on that carbon right there? So it's got two hydrogens, then it's bonded to this carbon here, and then it has a lone pair. So it's got 4 domains that are around it, right? So I hope you said it was sp3. What's the hybridization of that carbon? So similarly, I hope you said sp2. And of this carbon here is sp. Now we know that an s orbital is spherical, spherically shaped. And we know that p orbitals are elongated. They look like dumbbells. An orbital is basically just a volume of space that the electron occupies. I know they say things like it's an area where inside of which you will find an electron. It's not inside of anything. The orbital simply is the electron. It's vibrating in these shapes, 3-dimensional shapes at the subatomic level. So they're like solid. So if you had an S and a P, you know that would be 50% character S and 50% character B. So if you were to combine what I just drew down here, the S and the P, it would be like half circle, half dumbbell shaped. So it would be like something like that. I should make the circle a little bit bigger, like about 50-50. What if we had an S and a sp squared? That means that orbital would have more p characteristic and less s characteristic. So that would be what, 33% s and 67% p? So that spherical shape would not be that prominent. It would maybe be smaller. And the p part of it would be, well, not that big, but maybe a little bit bigger. And then I won't even bother drawing it, but sp3 would be something that's way more p character than it is s character. Now, you know that the s character, the spherical shape of the electron orbital, is closer to the nucleus of the atom. Because it's closer to the nucleus, and the nucleus has protons and electrons, but protons are positively charged, they're going to be able to balance out the negativity of the electrons quite well. If something is more p character, then the negative charge that the electrons have are further away from the positively charged nucleus. The nucleus has protons and and neutrons. Neutrons don't have any charge, so it's just positive charge. So if you have a positively charged nucleus and a negatively charged electron that is more further away from it, then it's not stabilized all that well. It's kind of like that bond length thing that we looked at. The further away you are, the more easily you break. So what's more stable, something with an sp character or something with an sp3 character when it has a negative charge on it? So I hope you said sp is more stable. So when you have a carbon that is an sp carbon with a negative charge on it, its nucleus is stabilizing that negative charge a lot better than carbons that are sp3 carbons or sp2 carbons. Because they're more comfortable being negative. They're more stable. Because they're more stable being negative, they are okay to give up their hydrogen atom. If it leaves, they're okay with it leaving. So the conjugate base, this guy, Cb, is pretty stable. The conjugate base up here, on the other hand, not stable because it has too high conjugate base is not stable because it has too high of a P characteristic. So between A, B, and C, what's the strongest acid? So I hope you said C. And then B is somewhere in the middle, and then A is horrible as an acid. So if all else fails, you couldn't do the atomic size thing, you couldn't do the electronegativity thing, you couldn't do the resonance thing, you couldn't do the induction thing, you go with hybridization. Usually it's not going to be that, it's going to be the top four. And hybridization is going to be by itself. But in terms of our ranking for what's the strongest acid versus strongest or weakest acid, it's going to be those top four things, and then hybridization is going to be the kind of least important determining factor. This was all acids, by the way. Bases would be, I'm not going to go through the whole thing now, but bases would be the exact opposite. So if I said what's the strongest base versus weakest base, and then I gave you A, B, C, D as an example, the first thing you would look at is, of course, atomic size, which is going up and down, right? Not horizontal, but vertical. So I hope you're saying that the strongest base would be up here. We said the strongest acid was down here. If that didn't help you, you would go to electronegativity, which is left, right. We said the strongest acid was to the right side. More electronegative is a good thing. So the strongest base would be over here, further to the left, and so on and so forth. So let me stop here. At our next GSG, we can go into this more if you want. If you have any questions, you can email me and I'll try and get back to you sometime this week. All right, thanks so much.